Good afternoon, everybody. It's my pleasure to introduce Dr. Matthew Gardner as our guest speaker today. Dr. Gardner is an alumnus of Virginia Tech. He got his PhD in 2008 from Virginia Tech, and also his master's and his bachelor degrees in 2008, 2005, and 2003. And Dr. Gardner is responsible for over 6,700 miles of electric transmission transmission lines and more than 800 substation assets at Dominion Energy, Virginia, serving more than 2.7 million customers. Since joining 2008, he has held different positions in the company, including planning, operations, maintenance, and engineering positions. Dr. Gardner serves on the board of the North American Transmission Forum and the Executive Advisory Council of the IEEE and its Power and Energy Society. He is president-elect of SIGRI US National Committee, and he's an active supporter of many academic institutions, obviously including ours. So without further ado, the floor is yours.
Well, thank you very much. I appreciate it. And it's okay if I walk around a little bit. What I'd like to do is I'd like to keep this somewhat conversational today. I don't want to just present facts and figures because chances are you probably already know all of the facts and figures. But there's a couple of things I think that are really important to realize as we start a conversation about energy. Our energy future isn't rocket science. It's more important than that. But let's go back to understanding, just so we're all on the same page, let's just go back to understanding the true value of energy. So I think energy is the barrier between chaos and order. Do you agree? Do you agree?
Absolutely.
You think so? So I don't need to explain that piece to you. If we think about there being two extremes in our universe, on one end you have chaos, right? And on the other end you have order. We can force those two concepts into extremes, right? What is extreme chaos? What is extreme chaos? Yeah. Extreme chaos is death, right? That's extreme chaos. What is extreme order? Tyranny. So maybe we need to think a little bit about, maybe we need to take ourselves on a thought experiment. Of course, we all know that over time, left alone, this system will mingle and devolve from the extreme of tyranny into chaos and death. And what is that called? What law of thermodynamics is that called? Is that entropy? Is that what that is?
Sure.
All right, so let's talk about us. Let's talk about us for just a second. The distance between us and death. Right now in this room, it's 72 degrees and fluorescent. On the other side of that window, it's 22 degrees and snowing. So let's do a quick thought experiment together. Let's go out into the wilderness. This instant, let's go out into the wilderness. Let's each one of us be transported remote from one another into isolation, into the wilderness. It is you and the wilderness. What is the first thing you do? Well, right now, if you've been transported into the wilderness, the distance between you and death has just gotten a lot closer, hasn't it? Right? I mean, right now in this room, the distance between us and death is fairly well managed. I'm not sure, but I don't think any of you is going to die in the next hour. And I certainly hope not to say anything that induces your death. Certainly not death from boredom. But if you were just taken and flung out into the wilderness, into the elements, the distance between you and death certainly starts to become closer. So what do humans do when they want to increase that distance between themselves and death? What have they done historically? What do they do today? They decide to leverage energy, right? The leveraging of energy increases the distance between us and death, establishes a boundary of order between where we live and chaos. And then throughout human history, we have done nothing but master that, right? There are lots of things present in this room today that have, with great efficiency and technical capability, increased the distance between us and death such that we can thrive. What I'm here to talk about and what I'm here to discuss with you is the fact that the miracle of electricity is really what has insulated our society from the chaos that otherwise abounds, right? So mastery of energy transport is certainly a border. It's a border between us and chaos. It's a border between us and death. I like to start off with that as a premise for the discussion. Now let me pivot from there into a little bit of a history lesson. I'll talk a little bit about Dominion Energy. I work for Dominion Energy in Richmond, Virginia. But let me pivot from the basis of energy, of the mastery of energy transport and energy usage as a barrier, to the history of the electric grid as we know it today. It is going to be a summative history. I am going to skip over some elements that are very, very important. We just don't have time. All right. So let's rewind back to World War II. Let's rewind back to the post-war era, right after World War II. World War II was a great catalyst for innovation, as horrible of a thing as it was for the world. It was a great catalyst for innovation. It opened up developments in material science and technology that really enabled the power grid as we know it today. It was in the early days, post-World War II, that we started seeing large, vast, synchronous electrical interconnections that we have consolidated essentially into 3 interconnections in the United States today. Those started knitting together at rapid speed right after World War II. Before World War II, a big generator was 30 megawatts. After World War II, a big generator was 300 megawatts. And then we eventually tortured enough energy out of steam to make units that are well over 1,000 megawatts and integrate those onto the grid. The nuclear age began. The nuclear age came about. And so by the time the mid-1960s rolled around, we had the ability to safely, what we thought was safely produce nuclear energy and leverage it for society. And so in the period of time between 1965 and 1985, all 97 units that are running right now today, essentially in that time period, all 97 reactors that are running today came online. And that came online. If you think about it, each one of them is about 1,000 megawatts. So you got somewhere along the lines of 97,000 some odd megawatts, maybe a little less. All of that came online in a 20-year period, give or take. What simulation tools did we have available in the 1960s and 1970s to design and build and construct large power grids? What types of tools did we have at our disposal then? Did we have cloud computing? Did we have PSSE? Towards the end of that period of time, we did have PSSE. Do we have PSLF, PSCAD, RSCAD, RTDS? Did we have What's the other one that's the RTDS competitor?
Simulink,
What's that?
Simulink.
There's Simulink out there. There's another one I'm thinking of. We have-
RT.
Opal RT. Who said Opal RT? All right, you win the first award, Opal RT. Did they have that? They didn't have that. No, they had pencil. There was some computational capabilities. You tended to have to speak to computers through punch cards, but it was a lot of pencil and paper. So what happened? The electric grid as we knew it then grew into something that was really kind of oversized, right? How did you bring reliability and certainty when you didn't have the precision of compute? You did it with oversizing your infrastructure. So the mid 1980s roll around. By that time, we'd had a couple of internationally prolific nuclear disasters. 3 Mile Island, which was not a disaster. Actually, they did everything wrong in 3 Mile Island, and the unit still shut down. And then, of course, Chernobyl. But that was the end of the nuclear renaissance. And we essentially had a grid that did not really require a lot of attention over the next 20 years or so. And it didn't get a lot of attention in the next 20 years. From 1985, mid 1980s, I'm just using 85 as a proxy, through 2005, again, just using that number as a proxy for those 20 years. We didn't spend a whole lot of time talking about the mastery of energy transport. We didn't spend a lot of time thinking about innovation as it pertained to the power grid. Power programs, your conventional power systems programs shut down across the country. At the nadir, I don't know how many were left, but I think, Dushan, how many? Maybe a dozen.
Yeah.
Power programs. Yeah, something like that. Virginia Tech was one of them. The sacred knowledge of power systems was retained at Virginia Tech. Of course, CPES and power electronics, but power systems was retained as well. And of course, now that we've had a resurgence from that. Well, what caused the resurgence? We were able to live on the fat of the grid and not focus too much on the mastery of energy transport, at least not at a bulk electric power system level. So what happened? Because that's not where we are today. There are probably hundreds of power programs around the country, tremendous amount of investment in the power grid, tremendous amount of research in energy today, and a tremendous opportunity for us to do even more. But what happened? Where did all that come from? Why? Well, the power grid didn't need a whole lot of attention until it did. August 14th, 2003 was the great blackout of the Great Northeastern Blackout, took out essentially Detroit over through to New York. It was caused by a number of overlapping failures, but essentially we'd pushed the grid to its limits, and we had decided not to invest in grid expansion and maintenance, and society paid the price for that in the 2003 blackout. That changed policies. It changed policies, which gave us mechanisms to invest in the grid, to earn a reasonable rate of return on those investments, so long as we did it safely, efficiently, and cost effectively for our customers. And then it also gave us a mechanism to perform maintenance on the grid so that we can keep the grid up and running. But that's not what I'm here to talk about today. I'm here to now talk about the new frontier that we're facing, and I want to unpack some elements of that today. So I'm going to hit some figures here, talk to you about a little bit about what our grid looks like today. So you're sitting in this room, and if you're online, you'll have to just look towards Northern Virginia. We're up here. I work for Dominion Energy Virginia. This is essentially what our footprint looks like. It covers in the state of Virginia, it covers about 6,700 miles of transmission. You see 10,600 over there. That's because we also have service territory in South Carolina. Nearly 80,000 miles of distribution lines, 4 operating nuclear units in the state of Virginia at two sites. Dominion has 4 sites total. So this is just a little bit of an overview of what our grid looks like today. And I show generation as orange gumballs and generation projects in the queue on this map as green circles or green gumballs. Let me ask you the question. Why are there so many more green circles on the map than orange circles on the map?
Power demand is soaring.
Power demand's going up for sure, but still, why so many? And why are there a bunch of small ones?
Distributed generation.
Distributed generation, renewable energy. So that's a snapshot. I don't want to spend too much time there. And if you wanted to take a peek at where our service territory is in the Commonwealth, this is the blue areas here highlight where we serve our customers. So about 65% of the residents in the state and 60% of their businesses get their energy from Dominion. Let's focus on.
Gets the thing in between.
Good question. So there's people.
I mean, that one is clear, but
Yeah, we have.
that's AP, but what about this one?
This is APCO here.
Yes,
This is First Energy here. But what about all of the people that live in the gray? What about those people? Where do they get their energy from? That's a good question. This is a common construct around the country. In investor-owned utilities, Dominion Energy is investor-owned utilities. And Dominion has been in business since 1909 in its current form. So we've been doing this for about 116 years. But investor-owned utilities tended, again, we're going back to the days right after Edison and Westinghouse, right? But they tended to crop up in areas where there were population centers. So Mr. Edison set up an energy company in New York and they called it Consolidated Edison. Similar company here was set up, Virginia Electric and Power Company, focused on powering Richmond, Virginia, and Hampton roads. And then across the country, Commonwealth Edison powers Chicago, on down the line. But what you didn't have served under this construct were the rural customers. Who served them? Electric cooperatives. So what you've seen roll out across the country was an infrastructure of rural electric cooperatives. So these customers in the gray area still get energy, and actually they still get it from Dominion, but they are a part of a cooperative. They buy their energy wholesale, and we serve it to them. We serve it to them at the retail level. We have a transmission system that is comprised of essentially 3 bread and butter voltage levels. 500 kV is our highest voltage. Our utility neighbors down to our southwest, their highest voltage is 765 kV. If you've driven to Blacksburg, you go by Cloverdale, you see 765 kV. We are extending from AEP into our service territory over the next few years, over the next 5 years or so. We're extending 765 kV technology AC into our service territory. We'll be extending 765 kV essentially up to this point here, So the Commonwealth's energy infrastructure is growing. I'll talk a little bit about those growth drivers. 3 bread and butter voltages. As you can see, most of our voltages are operated at either 500 kV, 230 kV, or 115 kV. And of course, we have some of the other voltage levels in between. But that's the circuit that it takes to essentially serve load in the Commonwealth across 900 substations. And there's a lot of growth drivers behind that as well. I'm not going to, again, I think Kathleen, these slides could be shared, so you can dive into some of this data a little bit later. But what I wanted to talk about is we started the conversation just by agreeing on the premise that the mastery of energy and energy transport has been able to essentially catalyze human flourishing through the establishment of a strong and solid wall between chaos and order. But I would say that we are now finding ourselves at the beginning of a transition that's putting the electric grid, especially the electric transmission grid, right at the center of progress where we from where we stand today. So let me talk about our growing thirst for energy. The thirst is terrific. What is driving energy use in the United States today? Data centers. Data centers. Why data centers and not why not anything else? Why data centers? Aren't computers getting more efficient? Aren't we? Isn't CPES making more efficient?
No computers.
But
Not computers.
the components that power those GPUs, those are getting more efficient. Why if computers are getting more efficient, why are data centers predominantly the driving force for energy growth in the US today? I'll just switch to this next graphic. I stole this graphic, by the way. Why data centers? AI? But can't we make the chips even more efficient? I think we have Jevons paradox at play here, actually. Has anybody ever heard of Jevons paradox? Jevons paradox? Just write that one down. Jevons, Jevons paradox. It's essentially this notion that the more efficient you become at using a commodity, actually the more of that commodity you use. And this is something that was actually discovered in England about 200 years ago. In England, they were getting worried about running out of coal because, you know, you had to dig for it. And, you know, everybody was using coal to heat their homes and to cook dinner. And all the cities were getting big. And it's just getting all this coal. We're going to run out of coal. And so about 200 years ago, there was actually a real push for much more efficient stoves. And guess what? They made much more efficient stoves. And guess what? Coal consumption skyrocketed. All right. About 20 years ago, we decided to, as a society, reduce, reuse, and recycle paper products, right? Paper products. Okay, so we don't print stuff if we don't need to. We use a lot of digital stuff. Guess what? Our use of paper has skyrocketed because you have a little button in your phone right now and you can prime something to your home and it's going to be delivered tomorrow and it comes in a cardboard box. Because as we've gotten more efficient using paper, our use of paper has gone up. More efficient use of energy, especially if you can take energy and you can turn energy into information, you can turn information into knowledge, and then you can take knowledge and make it intelligence. There is no limit for controlling that cycle. It's not like, okay, I have enough intelligence now. It's not like intelligence is a refrigerator. All right, I got one. I'm good enough now. It's no, I want more. I want more scenarios analyzed. I want more things forecasted. By the way, we did the same thing with cars. We developed rideshare apps so that you don't have to have your own vehicle now. You can Uber wherever you need to go. Guess what? We've got more vehicles now because you have a vehicle and you Uber. So anyways, Jevons paradox shows up quite a bit. So let me talk about data centers. Northern Virginia, okay, how far away is Ashburn from here? Is that about 20 miles to our west? Dulles Airport, is that about 20 miles to our west here? Something like that. So go 20 miles west to Dulles Airport and then go about 3 miles north of Dulles, all right? Or next time you're flying in from the west, you're coming in on the westerly approach, look out your left window. That's Data Center Alley. The industry calls that Data Center Alley. That's the largest data center market. What you see out of your plane window, everything you can see right there, nothing more, nothing less, everything right there out of your plane window, that's Data Center Alley. And that is the world's largest data center market. World's largest data center market. There's enough data centers in there to outweigh the next 4 international data center markets combined. International data center markets combined. It's larger than the next 5 domestic data center markets combined. So we're sitting right on top of Data Center Alley here in the Commonwealth. There's some legacy reasons why, but I'll leave it at that. By the way, every data center has backup power because nobody likes to go without their YouTube, Netflix, Amazon Prime. So there's always backup power at these data centers. About 150% installed backup power at these data centers. And those backup energy sources are emergency diesel generators. So we have the world's largest collection of diesel engines in the world as well in Northern Virginia. So just to give you some megawatts and some growth rates here. All right, so Northern Virginia, this is the biggest market. Around the time of the pandemic, 2,500 megawatts. We've added about 1,500 megawatts to that already. We're sitting around 4,000 now, and we're on pace to go up to nearly 8,000 megawatts of demand just in that one data center market. 8,000 megawatts. How much energy is a megawatt? How many homes can you power with 1 megawatt? How many homes can you power with 1 megawatt? I don't know. You tell me. Well, maybe I do know, but I'm trying to be. How many homes can you power with 1 megawatt? You have any idea? Throw a number out there. Oh, he's so good. He's 200. Yeah, about 250 homes is a megawatt.
Wow.
250, about 4 kW per home. Average. All right. Now, if you're out there, if you're making dinner and all this other stuff, you know, you're going to be pulling more than 4 kW. All right. So that's the data center. That's the data center market. And I just put some pins on the map here to show kind of how data centers are clustered in and around Data Center Alley, but they're starting to develop and come down I-95. Big ecosystem here. And we're getting a lot of requests now. So each year we get requests. We call these DP requests, delivery point requests, because data centers, they want us to deliver energy to them. So they give us a point where they want energy delivered to. This, look, in 2020, I got requests for 21 delivery points. Not all of these are data centers, but predominantly they are. Okay. And look at the capacity. 21 requests asking for 2.9 gigawatts. That was in 2020. All right. Last year, I got 74 requests totaling 15 gigawatts. So 3, 7, 16, 26, I got 40 gigawatts of capacity requests that we're sitting on top of today. That's what's driving worldwide energy usage. That's the data behind the numbers of data center driven energy demand growth. So what does a data center look like? By the way, I told you, look outside your window when you're landing at Dulles Airport. Look out to the left. This is what you see out to the left here. Pretty much every single one of these large buildings is a data center. Data centers today take up about the footprint of an aircraft carrier. What's the power density of an aircraft carrier? I'm sorry, that's classified. You've got to go up to the 7th floor to hear that number. But I have a guess. I can share it with you. I bet an aircraft carrier's max load's about 150 megawatts of an aircraft carrier. All right. I was up with Dr. Richard Zong. We were talking. We put my ear to the ceiling, and that's what I heard up in the sky. I guess I got to be careful. I'm joking. I'm joking. All right. But 150 megawatts, that's about what a data center is. So data center is about the size of an aircraft carrier in terms of the land space that they take up, about the energy density as well. And we're at the point now where when a data center of this size comes to our system, which this is fairly typical, it requires a substation. It requires a substation. I'm going to need your help, and I only think I can tee up this appeal today. But I'm going to need your help in coming up with innovative ways to serve this type of load. Do I need to be feeding these data centers? Do I need to be feeding them AC in the future? Can I be feeding them DC? Can I make these data centers, as opposed to just a load on the grid, can I make them a benefit to the grid? Those are the types of questions that we're trying to answer. Can I make these data centers more than just a societal benefit for our customers, but a technical benefit, something that can help them pay their power bill? Those are the types of questions we want to leverage the engineering ecosystem. So this is a substation. I won't go and point out all the little parts and pieces, but that's about 150, 200 megawatts of infrastructure right there. Questions about data centers? The Innovation Campus, Virginia Tech Innovation Campus, down in, what do they call that? Not Potomac Yards anymore, National Landing. National Landing. That 11-story building is 300,000 square feet. I just got a tour this morning and it is awesome. Data centers, about half that building, but all on 2 or 3 floors. 50 to 100 acres per site. I talked to you, typically need an on-site substation. And not very worker dense. And that's actually one of the ways you can tell a data center is a data center, especially if you're looking out the window like I told you to do at Dulles Airport. You don't see big parking lots outside these places. It doesn't take a lot of people to run a data center. 20, 30 technicians keeping those servers up and running. So I've talked to you about some of this. These numbers, as I said, they've gone up. Now we're serving, right now, we've got about 5.2 gigawatts of data centers on our system. It's about 25% now, 25, 26% of our retail sales. And they're growing at a clip of 500 plus megawatts per year now. This is our data center growth. Again, I actually have a graph that's been updated. This is through the end of 2022. I just looked at the graph yesterday. It's been updated. I just didn't update this particular slide, but we're on track. Our projections are essentially lying right on top of the actuals for 23 and 24. So we're sitting here at 25. And again, this is for our Northern Virginia. And then if we start to look out towards the end of this decade, we're looking at about a doubling, and then a doubling again, and so forth, really every 5 years or so. So that's the thirst of energy for data centers. One thing that I think is really interesting is we're seeing peak load growth on our system. Back on January, I want to say 23rd, yeah, it's right here, 23rd, we had an all new system peak. It was 11 degrees that morning, and no solar on the system because it was pre-dawn hours when we hit that peak there. 24,678 megawatts on our system. And as you can see, these are our top 10 peaks of all time. Guess what? They've all happened in the last like 7-8 months. So we're continuing to set new records for demand on our system over and over and over again. So how do we power that? How do we energize that? How do we meet the growing energy demand? While data centers are certainly driving the load growth in the Mid-Atlantic today, we are just getting started in other electrification verticals. One of the things that's really interesting is, anybody ever live north of here? New York, Pennsylvania, New England? Anybody ever live out that way? When you lived out that way, what did you heat your house with?
Pretty sure it was, I was renting, but I'm pretty sure it was natural gas.
Natural gas, yeah. One of the things that's happened is heat pumps have gotten extremely efficient. Jevons paradox again. If I can extract heat out of 0 degrees outside, why heat with gas when I can heat with electricity and have an all electric home? So north of here, we've had heat pumps in Virginia forever. I say forever, since they've been a thing, 70s and beyond. But north of here, they really haven't, because they might have had air conditioning, but they didn't have the heat pump. Now we're starting to see heat pumps become very popular all the way up into New England, actually. Very high efficiency. Electrification, transportation. Look, we're just getting started. We've seen some significant trends, but this is still in the noise for us in Virginia. If and when electric vehicles pop, there's going to be other upward pressure on energy demand as well. So let's talk a little bit about the energy transition. Let me just catch myself up here on my notes. So I like to think of the energy transition as having three components, and you're involved with each one of the three components in electrical engineering. There's electrification, we talked about that, right? There's digitalization, or let's just say datafication. That is the predominant use of the growth of energy use for data centers. And then of course, decarbonization, that's greenification. So these are the three features of our landscape that are changing and changing significantly. And I really see each of the drivers as falling into one of these three buckets. On the generation side, again, this is last year's slide, but still pretty certain, especially here in the Commonwealth. The blue dots show generation that is in service at present. The gray dots are projects that are in the queue. What does the queue mean? If you want to connect onto the electric grid, if you're a generator that wants to connect onto the electric grid, you don't just connect to the grid. We need to understand what type of generation you are, what's your rating, what's your performance. And then you get in line and you wait for the grid to be upgraded so that it can receive your energy, right, reliably. So if you look here, the blue dots are in-service generation. The gray dots represent generation that is in queue to come online. So that means it'll be online in the next 3 to 5 years. One of the interesting things is there's a lot of gray dots where there aren't other dots, right? There are large areas where I've got some pretty big dots that aren't near other large dots. And the reason the proximity of these dots is important is because if I've got a big dot, if I got a big blue dot, I've got infrastructure. So we're having to kind of wire the grid out to accommodate generation that's coming online. So I just wanted to kind of call that out in terms of while there is some overlap, by and large, generation is coming where it has not historically been, and that's because the type of generation. Now, I've showed this slide a couple of years ago to Dr. B, and he told me it was wrong, and he's right, it was wrong. And I'm going to tell you what it should look like. But this is the food pyramid for us today in the energy landscape. This is our energy supply pyramid. Okay, right now, most of our customers at this very instant, as I speak right now, most of our customers are being powered by a resource stack of gas, nuclear, and coal, a little bit of solar, getting towards the end of the day, and a small amount of wind. This is essentially how the energy pie stacks up today, all right? I just showed you a map that showed the generation interconnection queue, where the generation is, where it's coming. That is effectively inverting our energy supply pyramid. Significant investments in solar, significant investments in wind. Where Dr. B told me I was wrong a couple of years ago is on the scale of these. Because this gas supply ain't going away. This area really is this area or larger. You see what I'm saying? And then maybe nuclear restacks a little bit, but you know, there's a tremendous amount. The energy demands of today are a larger triangle than they were yesterday, and the energy demands of next year will continue to scale this triangle, scale this triangle up. So the trends are electrification, greenification, datafication, changes in generation. What does this mean? Well, this is adding some, the inversion of our energy pyramid is adding some technology changes that are really changing the world in which that we have to deal, changing the world we have to study, changing the world we have to analyze. Okay, when I first started in this industry, not that long ago, I got my undergrad in 2003, so I've only been doing this for like 22 years. But when I started, there wasn't a lot of physical uncertainty on the generation side of an equation, right? These were large rotating machines. There ain't but so many ways you can mess with the controls of that thing to make it look physically different to the grid, right? You can play with the exciter models and you can play with some gains here and there in governor settings, but the envelope is pretty fairly well defined in terms of how that generator can show up on the grid, all right? Inverter-based generation is very different. It's magical in a way, right? If I'm an inverter, I have a much broader envelope, parameter envelope, that defines how I look technically to the grid. And I didn't have that in the past. So there's some physical uncertainty as I've gone from large rotating machines to electronics-based generation or inverter-based generation. Our industry's struggling with that. We're trying to standardize that. We're trying to, but the whole issue has been when this type of stuff, when solar first started coming onto the grid, it was such a vast minority of the resource stack that the idea was if there's a problem with the grid or if you're having a problem, get off, get away, trip, go away, be gone. I don't want that behavior anymore. If the grid's struggling, I need you to hang on and help, right? I don't want you to go into momentary cessation or to trip. So there's some physical uncertainty. There's also some radically increased scale and dimensionality. Radically increased scale and dimensionality, right? The grid, think about this. I can fit a 1,500 megawatt 3-on-1 combined cycle unit. Everybody knows what 3-on-1 is, right? 3 gas units and then a steam unit that uses the heat recovery steam generator to add a 4th to the grid, that kind of thing. 1,500 megawatts, okay. I can put 1,500 megawatts of iron and steel essentially on 100 acres. All right. If I want 1,500 megawatts of solar, I'm likely not getting it from one site. And in this part of the world, it's roughly 6 to 10 acres per megawatt. So I need 6 to 10 acres of land with solar panels covering those 6 to 10 acres to get a megawatt. So to translate that to 1,500 megawatts, I'm not great at math, but 1,500 at 6 to 10 per megawatt. I mean, I'm talking hundreds of thousands of acres, all right? So that is a radically increased scale and dimensionality. So I'm likely not getting it at one site. I'm getting it at different points on the grid now, right? So this is a challenge. And then we've already talked about the digitally modulated resource interfaces. This is really where innovation in the power electronics space, I think, is going to save the day for the power grid of the future. I think grid 3.0, as I heard Dr. B describe it, is a grid that doesn't operate like water sloshing downhill in whatever pipe it's going to flow in. But I think the grid 3.0 is going to look more like an energy routing system. It'll look like an energy routing system. And so we have both the advantages and the challenges with those digitally modulated resource interfaces. I try to explain this. I don't need to explain this to you because you all have a technical basis that's elevated from most. But if this is conventional generation over here, all right, on the scale, and this is inverter-based renewable or any inverter-based resource, I don't care whether it's renewable or not. A megawatt is not a megawatt, right? 1 megawatt over here does not equal 1 megawatt over here. There's a difference, right? There's a difference because over here with conventional generation, I'm not just getting a megawatt, I'm getting dispatchability, compact control. That is, I have one controller on that 100-acre site that controls the whole thing. The site's controlled. It has inertia. The model is mature. I know how to model. I know how it's going to show up in in simulation. And I can do all sorts of stuff. It's going to give me fault current. When there's a problem, it's going to rush fault current in. If I want that over here with inverter-based generation, I need to strap on a lot of technology, right? But there are costs with that. Not only costs, but there's complexity. We're going to figure this stuff out, but it's challenging. And so to power our digital energy future, we need to figure some of these things out. I'll leave this for you, but these are all things that we probably understand, right? That we could see changes in system inertia, power quality, right? System strength, system restoration. And what I want to leave with people is, you know, today I think of the power grid as this big vehicle here, this big 18-wheeler, right? I just found a Dominion one because I wanted the logo on there. I mean, this is really not the biggest, heaviest, big rig I could do, but this is the power grid today, right? Power grid today, it's like a big rig going down I-95. I don't know how many tons it is, but it's a lot. And you know, when it gets trucking, and it's hard to perturb that thing, right? But it's the control principle of the inverted pendulum, right? I've got this big mass at the top of this pendulum. If I do get that thing unstable, it's really unstable, right? That's the grid today. The grid of tomorrow, leveraging power electronics, advanced controls, is like a fleet of Formula One cars. The grid's going from being big, heavy, and lumbering to light and sticky. And there's some advantages there, but it takes innovation. It takes intentionality. It takes your help. I need your help. I really do. Oh, now we're getting into, does anybody like Legos? Anybody like Legos? Anybody play with Legos? Yeah, just me? All right, well. So I've talked about some of the things that are driving load growth. I've talked about, you know, some of the digital components of that. But for those of us whose responsibility is to design and to build the grid's really kind of stick-built today, purpose-built today. Lots of custom infrastructure. At Dominion, we're looking at innovations like what we're calling grid bricks. We want to call them grid Legos, but we thought we might get sued by Lego. So what can we do to take infrastructure and make it modular, prefabricated, rapidly deployable? If we can start building the electric grid with components that are like proverbial Legos, then not only can I build it more rapidly to serve this rapidly increasing load growth, but then also when there's a problem on the grid, when we have that natural disaster, when we have that wildfire, when we have that hurricane, when we have that terrorist attack, guess what? I just go back to my Lego bin and start to put parts and pieces of the grid together again. In order to do innovations like this, I was talking with Dr. B about 10 years ago, and he said, Matt, you need a high voltage lab. And so I wrote it down, and I came back 18 months later. And remember, we were in third floor of Whittemore Hall, and we rolled out the plans. What do you think? You need this. Dr. B gave us a lot of free consulting on how we needed to lay this out. It doesn't need to be one building, it needs to be two buildings. But we're actually this is our high voltage lab. This is about 45 minutes south of Richmond. We're really proud of this lab. We see this lab not as technical insurance, but technical assurance, because the grid of the future is going to have technologies that are flexible AC transmission systems. It's going to have HVDC. It's going to have medium voltage DC. But there's a lot of material science that needs to be done. There's a lot of manufacturing that needs to be done. Almost none of that is done in the United States today. And we need the technical assurance so we can deliver tomorrow. So we've made the investment in a high voltage lab. So we're proud of that. So I had to show a picture of it. Hey, Dr. B, have you been there yet?
Yeah, well, not since the thing was finished, yes. 6 months ago.
Yeah, well, yeah, because you came for the Dr. B is here. Yeah. So Dr. B's signature is way up in here somewhere. The beam signing, remember we were talking about the beam signing, Kathleen? You went to the beam signing over there. This was our beam signing. Yeah, we're proud of that. That's about the same size, by the way. There's a tree and there's some, this is about the same size as the, just to give you guys a sense of scale, this is about the same size as the Innovation Campus.
Oh.
Yeah, this thing's about 180 feet tall. Yeah, high voltage lab. We're really proud of it. This is a gem for the Commonwealth of Virginia, certainly for our customers, but also for our nation. This is our technical assurance. This is how we're going to do it. And of course, you always have size matters, right? When it comes to high voltage labs, size matters, and we're the biggest in the country. You know, we're proud of that. We're up here. This is the size of our lab. Mississippi State has a cute one.
Matt?
Yeah.
Missing Virginia Tech logo on the.
Yeah, we're.
I tried to get them to paint it maroon and orange, but they just wouldn't go for it.
I'll spare you the glory.
Actually, that's a compliment to me, because they have included us from first idea. And we do have space there to do the real research.
There is dedicated space for Virginia Tech offices and cubicles. So who wants to sign up and come work with us?
And get electrocuted.
Yeah.
Sign up.
No. It'll be fun.
This is what the inside of our lab looks like. The test equipment, again, we're just starting to put the test equipment together, commissioning. We're going to be, this summer, we'll be commissioned, ready to go.
But yeah, end of May, first week in June, we'll be ready to go. This is the DC test set with the chop wave over here.
Yeah.
AC test set will show up end
Chop
of
wave.
March, early April. They'll put it together and be commissioned in May.
So we're excited about this. Again, lots of value for the Commonwealth, lots of collaboration here. I can't talk about the opportunity and the growth and the needs without hitting the threats. And I promise I'm coming around the fourth corner on my talk. You guys, it's almost 5 o'clock. It is, it's hammer time, right? In Blacksburg, there used to be a place called the Cellar, and hammer time ran from 5 to 7 every Sunday through Thursday. You could go to hammer time, you get a pitcher of beer for $5, and so we would learn a lot.
Obviously, you were in graduate school.
I did graduate school then, yes. Look, the 21st century turns out to be a pretty dangerous place. And every time I do this presentation, I have to add another bullet on here. And I wish I could start taking some of these bullets off. While I can't take bullets off, I can defang them, and I can defang them with innovation and resilience. I'll talk a little bit about how I can do that. So I'm not going to drag you through all of these, but cybersecurity, insider threat, lots of intellectual property theft, geomagnetic disturbances, interference, sabotage, physical threats. The list goes on and on. And this is another slide that I wish I didn't have to update. As a matter of fact, I haven't updated in the last year, but there's been some stuff that's happened even in 2024 that really belongs on this list. So how do we deal with this? We try to stay in this cycle of assessing what the threats look like, preventing them through measures such as physical security programs, EMP hardening, dealing with flood risk by elevating our infrastructure when we do rebuilds, leveraging gas insulated switchgear. I'll show you some pictures of all of this stuff. Detecting threats and then recovering. Recovery is the key to turning reliability into resilience. Recovery is the key from turn reliability into resilience. The lights are going to go out. The lights are going to go out. The question is, how quickly do they come back on? And how fraught is that process when there are complicating factors and there's damage involved? So what are some of the things that we're doing? We lean in heavily on lab testing. This is the only energized 500 kV energized geomagnetic current injection testing that's ever been done in this country, in this hemisphere, at our Carson substation. So we took energized transformers and we ran how many amps of DC? 1,500 amps of DC into the neutral of that transformer, and said, let's see how it performs on the grid. And so we got great measurements from that. Obviously, I talked about the high voltage lab earlier. We also spend quite a bit of time hardware in the loop testing, our RTDS NovaCore setup that we leverage. These are some of the ways that we assess the threat, right? We prevent the threat by trying to make our infrastructure not appear to be a target or not appear to be a soft target. So we leverage things like hefty fences. As I talked earlier, we like to elevate infrastructure when we can. When it makes sense, we put infrastructure inside a building leveraging gas insulated switchgear technology. So this is an entire substation building. Remember the one, Kathleen, we were looking at earlier? Hey, there's a substation. Well, guess what? You can put one of those in a building and you never see it from the street. That's a hardening measure. EMP protected control center. So that's a EMP Faraday shielded control center. We detect the threats. We've built. Dr. B, have you been to this one? Have you been to our market? You got to come visit. Y'all all got to come visit. This is our monitoring analysis and restoration center. This is a cathedral to data analytics. Rule 0 of data analytics is look at your data. Well, I have the largest Sony 8K screen that they have ever built, at least as of the time I took receipt of this one in our mark. This is our cathedral to data analytics. We're leaning into data analytics. We want to give our employees the resources they need to dive into the data, the tools they need to extract value out of that, and to make us better. Obviously, you got to watch what's going on and lean into automation. When you have faults on the system, where are the faults? What do you need to fix it? So that's detection. Recovery. We're pretty proud of this. I'll show you some more pictures about recovery here in just a little bit. That's our mark again. Here's a good example. This is a substation here that's made out of mobile components. This is one big picture along the bottom, and these are three smaller pictures with some of the subcomponents. Gas insulated switchgear on the inside of these trailers. Essentially what I could do, this is going back to, remember that I talked about that grid Lego brick? This is what grid Lego bricks look like. We're looking to try to expand essentially this basis into larger technology and into larger bricks for the grid. So this is essentially a scenario where I had a grass field one week and the next week I had a substation. I was able to roll, these are transformers right here. You don't see the bushings because it's all oil to gas bushings here. Switchgear, again, another transformer, controls. And this is it's not like just like, well, this is Matt coming to talk from us. He's from Virginia, he's from Dominion. I'm sure they do the same thing, every utility. No, this is how the Commonwealth is leaning in. We have a particular mission to provide our customers with reliable, affordable, increasingly clean energy. But oh, by the way, we've got to serve the nation's highest concentration of defense critical energy infrastructure as well. So we've got to lean on innovation to make ourselves as resilient as possible. And a lot of that looks like mobile hardware and mobile equipment. Let me just talk a little bit about CVOW and then I'm done because I'm already over time. We are right now in the process of building our country's largest offshore wind farm. It sits essentially between 25 and 42 miles off the coast of Virginia. 176 offshore wind turbines, all about what, 14.8 megawatts?
14.7 with a 15.2 burst.
14.7 to 15.2. So essentially call it 15 megawatts per turbine. Anybody seen offshore wind turbines before? Like in the flesh, you've seen it, you've looked at it, you've seen it. Yeah. Dr. B has. Anybody see them on land?
Yeah.
Okay, all right. These guys, the ones you see on land tend to be between 1 and 2 megawatts. So these are 15 times bigger. The swept area of the blades is 10 acres. So 15 megawatts, multiply it times 176, you get about 2,600 megawatts of power off the shore of Virginia. These are the monopiles that are being delivered. Those get driven down into the seabed. Of course, on top of the wind turbine, you have your nacelle, and then you have your blades up there. This is an offshore substation. We'll have 3 of these offshore substations. This one right now is parked down in Hampton Roads. We've taken delivery of it. We're getting 2 more. They're made in Denmark. And this is our offshore wind installation vessel. This is called Charybdis here. And this thing is jacked up they're doing testing of it right now because this thing, essentially goes out, jacks up, and installs your wind turbines. This is another picture of our substation. That's the substation itself, and then of course this is the support structure for the substation that'll be placed into the water.
To give you an idea of size, one blade is the length of a football field.
All right, so it takes a lot. I'll skip through some of this, but it'll be in the materials that you can flip through. But we'll have leverage underground cables. So this is what it takes to get. We'll have 9 of these guys. This is what it takes to get one of them. You drill in and you push in a pipe casing, and then pull your cable through. So significant infrastructure to get these guys wired up onto shore. And there you see multiple operations, direct pipe operations going in parallel there. Big civil work. And then, of course, you need splice bays, or what they call transition joint bays. These concrete structures are essentially where the splicing for the cables between the offshore cable and the onshore cables are made up. I know it's a little bit of information overload now, but just wanted to give you a feel of the scale of an operation for bringing on offshore wind of the magnitude that we're doing here. Again, 2,600 megawatts. That's like 3 nuclear units, three fairly large nuclear units. And then your cable, once it gets onshore, this is again a single phase of cable, 230 kV XLPE, cross-linked polyethylene. I already talked about our monitoring, analysis, and restoration center. We're also looking at other innovations that can help us better get data about the grid into our servers. So we're investigating right now private LTE and 5G to see if that makes sense for private network investments. And then I'm wrapping up this talk today with just a nod back to Virginia Tech, because the synchrophasor measurement unit was invented at Virginia Tech in the 1980s by Dr. Arun Phadke. And that has been a cornerstone for grid monitoring as we know it today. Synchrophasors, right? GPS time synchronized phasors. These phasors, essentially you get 30 phasors per second. Of course, we're going to even faster data today, but we've had a long history of investing in synchrophaser data for the better management and operation of our grid, really since 2009 or so. We've made some significant investments. It costs money to do all of this. Just in my business unit alone, we spend over $2 billion a year. And sometimes people ask questions, $2 billion just for data centers? No, it's not just for data centers. These investments support all of our customers. So as we've been investing, as you can see here, as our dollars have gone up, see the green is the low number, the red is the high number. As our dollars have gone up, what we've also seen is our reliability numbers come down. As a matter of fact, last year we had our best ever in terms of reliability, under 4 minutes of timeout on our transmission system. So our customers are realizing as we invest greater and greater reliability from the grid. So we're all benefiting. So your role, back to chaos and order, death and tyranny. You stand right here today with me. I need your help. You're going to deal with a lot of chaos. You've got a lot of stuff in front of you. And your role in electrical and computer engineering, especially the grad students that are listening and professors, is to take that chaos, to add your intelligence to it, and then bring order to this universe, this world of chaos. So that's me right here, Matthew Gardner. You can email me, send me your resumes. I've got to get something out of this, right? I'm a proud alumnus, but I got to get something out of it. Or, check us out at careers.dominionenergy.com. This wasn't a recruiting pitch, but I have to ask since I'm here, would you consider joining us? All right. Thank you for your time and attention. And if you don't have a question you want to ask here, you're not going to offend me by not asking a question. But if you do have a question, don't hesitate to email me or to give me a phone call. I think I'm available on the LinkedIn. I think I'm there on the LinkedIn. Yeah, question.
We discuss nuclear.
Yes, nuclear is a part of our future. Yeah, and you're right. There's so many things to fit in there. I just didn't spend time on it. But we are definitely looking at nuclear energy. A couple of things I'll draw to mind. Small modular reactors. Yeah, our North Anna site, we're obviously partnering with the state to develop an SMR at North Anna. And I'm sure we'll see in time further development of SMRs. We also just recently announced Commonwealth Fusion Systems is working on the development of our nation's first commercial fusion reactor. And we have worked with them to identify a site that would interconnect onto our system. So nuclear is a tremendous component of our future. And if you start to look at our so we file every year a integrated resource plan, okay? And that plan, really starting in the mid 2030s, is actually leaning pretty heavy into nuclear.
And in addition, we are working on a pilot with a company called Mindspring, which is generation that uses multiple fuels, particularly hydrogen. So we're looking at combustible hydrogen as a possibility, because you saw the amount of solar we're going to put in. Well, on a sunny day, that's going to be constrained. You're not going to put 50 gigawatts of solar into the grid. If you look out west in the WEC page, there's like 90 pages of solar that's cut off in the middle of the day. So you can use that time period in order to make combustible hydrogen that you can use to lower costs, and also it's environmentally very friendly. So we're looking at all the above for generation north.
Good question. Anyone else? Yes, sir.
So my question is Dominion Energy operating some HVDC transmission lines, and what is the current applied protection strategy for those HVDC transmission systems, even the multi-turbine?
Yeah. So right now we do not have any HVDC in Dominion Energy. I would be surprised if we do not end up having HVDC on our system in the next 10 to 15 years. So I think it's coming. Today, most conventionally, for most HVDC systems today, when there's a fault, you protect it by opening up the breakers on the AC side.
Yes.
Yeah. So there's definitely a need for converter architectures and technologies that can elegantly deal with DC faults.
Yes.
Yeah, you hear about the DC breaker,
And the full bridge converters.
Yeah.
We bought the leases 100 miles offshore of this offshore wind project. And the only reasonable thing to do is to use HVDC. So we see it in our future as a definite possibility.
Yes.
And I know you're working on that. So
Yes.
there's a bright future for you.
Thank you.
We're also heavily involved in development as an engineer. The opportunity for you to work and grow with other people in the industry and IEEE, we absolutely encourage our engineers to seek out others, new ideas, work with people that do what you do in other utilities. We do it also internationally through either IEC as well as CGRE, which is an international organization for large power systems around the world, to work with your colleagues in literally in the development of all of these new technologies, as well as, the big thing, try and reduce emissions down. So that's something else that you don't see a lot of utilities doing, is investing in their people. We see the people as the most important investment that we have. So if you want to continue to grow, it's a good place to come.
Other questions? Yeah, appreciate your time.
I
Yeah,
have
please.
two questions. The first one is I've heard the V2G, vehicle to grid, many times, especially many papers in IEEE.
Sure.
Exploring
Yeah.
engine. Seems that it regards the electric vehicles as storage resources. Whether right now it is already considered as storage resources, or is it, we are waiting for more vehicles in them.
Is that a question or a statement? I mean, I think you're right.
Like whether Dominion already do some demonstration or experiment or on that.
Not a tremendous amount of work on the vehicles as a storage mechanism. What we have done in that area is through our electric bus program, because if you think about buses, they're excellent candidates for electrification, and also excellent candidates for helping out the grid, because where are all the buses parked in the summer, right? They're charging, they're connected to the grid, and they got batteries that they can use for times of peak load. So there's been some work there, but I think we're still waiting for the ecosystem, the grid integration ecosystem, to mature a little bit more, so that technical handshake between the grid and battery resources that might be an electric vehicle can be fully realized to the grid's potential.
There's a lot of debate about how to do it because of the infrastructure upgrade that's required. When you're charging the car, it's a relatively low current. In order to push that through the grid on a larger scale, you're going to have to upgrade the transformers or even the service wires in many of the houses. Up north, where they didn't need a lot of air conditioning, the 100-amp services won't accommodate that. So it may be regional in the south, where we have a lot of air conditioning. We have much larger services at the homes that you can do that in, but maybe as a demand side management to be able to reduce load, on an individual basis at the homes. A lot of that's being looked at and played with in pilots right now, but in order to have a significant impact, you're going to have more proliferation.
And my second question is, I'm interested in Dominion has, like, you need to simulate a pretty huge system, like all of the Virginia substations, transmissions. Could you give us some impression how the simulation system look like? It's a supercomputer, it's a cluster of computers, or how it's?
Yeah, so we a few different answers to that question. We do use an RTDS system for targeted hardware in the loop and targeted studies for certain subsystems within the transmission grid. Interconnection modeling, we leverage PSSE. PSSE you can run on a desktop computer, but if you want to do a lot of scenarios quickly, you then need to move into a virtualized environment. And so I wouldn't so much call it as a supercomputer as it is a large server cluster.
For certain jobs, such as using finite analysis for magnetic induction, we have a Maxwell 3D model that we've got a 36 core laptop you run on, but it takes almost 3 days to do the simulation or something like that for either fluid flow, thermodynamics, electric field, or magnetic field. Having more power, certainly getting quick answers like that to know even if your model is developed correctly. After you finish developing SolidWorks, you run it for 3 days and then you find out you made a mistake. It's like the old days when I used to submit my cards and I'd wait at the station for an hour or two and I'd pick up my printout and realize that the cards are out of order, it's the wrong one. I'd have to go back, wait in line. So anyways, the time that it takes to do that is difficult, but there's a place for that in the coming future. Sorry, I gave up my age there.
Another question?
Thank you all. You've been more than gracious hosts. You've been more than kind to put up with me. I didn't see anybody fall asleep, but I gave you plenty of opportunities to do it. And you didn't. And so maybe do we have medals for everyone in here for having survived this? Thank you very much for your time. Really appreciate it.